Welcome to the GOTO podcast. Each episode covers the brightest and boldest ideas from the world's leading experts in software development. Tune in for practical lessons, compelling theories, and plenty of inspiration. GOTO gathers the brightest minds in the software community to help developers tackle projects today, plan for tomorrow, and create a better future. Stay up to date with the latest in tech through GOTO's top-rated events held online and in person in cities like Amsterdam, London, Copenhagen, and Chicago, and by subscribing to the GOTO Conference's YouTube channel, where you can find thousands more high-quality dev talks. Learn more at gotopia.tech.
Hello everybody, I'm Olimpiu, a curious technologist, and welcome to GOTO Unscripted. Today we have Felix in front of us. He is one of the rock stars, in my opinion, in the data space. He built Planetary-Scale data systems, and it's about to dive into his experience and see what we can learn from his knowledge. Felix, please introduce yourself.
Hi, Olimpiu. It's great to talk to you again. Always fun to have a conversation with you. See what you're up to, and happy to see where that one takes us.
Yeah. So last time when we spoke a couple of months ago, you were tinkering with replacing RocksDB as the core, the engine of the data system that you and your colleagues put together with DuckDB. But before we go there, maybe provide more context. You were in the team that put together the derived database actually from LinkedIn. So more or less it's the data that is the place where the data is stored about the recommendations, if I remember correctly, and so on and so forth, right?
Yeah, that's right.
Maybe if we do like a cut through it, what will be the main pieces if we are looking like to abstract away a data ingester, and then how will this data system look like?
Yeah. So Venice, the system that I have been working on for the past decade, up until recently, I left LinkedIn a month ago, but it was a distributed database, which we could say was part of the category of databases that we call unbundled. So that means each piece of the database is kind of a separate standalone component in a sense, right? So one big part of the database was Kafka. Actually, internally, we were in the process of replacing it with something else, but we can say it's just a pub sub, right? But I'm saying Kafka as that is what people are familiar with. And that was our write-ahead log component, and also our commit log or replication log between the replicas, right? And then we had servers, which internally were made up of essentially a Java process that had a RocksDB database locally. And then it could serve requests across the network, but it could also do certain computations inside of the server itself. And then there was a kind of a whole ecosystem of clients around it, like various client options for accessing the data. So you had a client that could send requests across the network to the servers, like kind of a typical client-server architecture as we usually have. But then there was also another client which had the same API as the remote query client, but instead, internally, it was actually embedding the RocksDB database, and it could pull data directly into the application process. We call that pattern the eager cache because it would eagerly load the data ahead of time. And essentially, that means your client application became as if it were another follower replica of the database, right? So you could set it up that way and then get even better performance. Of course, there is a resource cost, right? Nothing is free. Like you would have the data in your local RAM or local SSD if that's available. So that's why it's faster, but it also costs more set it up this way. And there were some other clients, like you could listen to the change capture stream. Internally, we had an ETL component to ship data to the grid. That part is not open source, though. Everything else I mentioned before is open source. Yeah, so that's kind of the high level architecture. And then, of course, there's a separate control plane apart from all of that decides on all of the metadata stuff, the partition placement, all that stuff. And it uses the Zookeeper and Apache Helix. So that's kind of the very high level view of the database. And circling back to the beginning, I said it follows the unbundled database pattern. Essentially, what I mean is like each of the component that I mentioned is a distributed system, right? So the write ahead log, let's say, is Kafka. Well, that's a distributed system right there. The server fleet, we had like, let's say, 1,000 servers per region or something like that. Those are, well, they were split across several clusters. Each of those are a full distributed system. The control plane itself is distributed, of course, for reliability. And the clients obviously are distributed. Like, we don't run applications that are just single instance, right? They are usually maybe an order of magnitude more clients than databases, or sometimes 2 orders of magnitude more. So every single piece basically is a distributed system. So that's kind of the high level architecture there.
Okay. Well, it's spinning in my head a joke, but I have to just drop it because now, given that while we are recording, there is another part of the infrastructure, internet infrastructure outage, Cloudflare is out. So a lot of its customers are back. So did you really have multi-zone? Well, you don't have to answer that.
Yeah, okay. We did.
Great.
Yeah, and we exercised it very frequently. Well, it's sort of like the chaos monkey pattern, right? That Netflix popularized. We essentially did what we called load tests several times a week, where we would fail out traffic out of data centers and concentrate the traffic into a single data center. Not all of the traffic, but like, let's say quite a bit. Like we were running in 3 data centers, and we were in a normal outage scenario, we would like essentially fail out of 1 data center, which means there are 2 left, right? And so each one needs to support more than 50% of its normal load, right? That would be the normal failure handling scenario. But during those load tests, we would concentrate it even more than that. So we would drain traffic out of essentially 1 full data center plus a little bit of the other, or roughly speaking, right? It's not exactly like that, but like in the aggregate, that's what it looks like. Meaning that the data center under test would get even more than 50% of its peak traffic. And we would do that in the morning, which is when in the weekday mornings, which is when we have our peak traffic. Okay. Regularly, right? So we would pick the time of day that has the highest traffic and concentrate traffic in a single data center. And we would regularly test that we can still sustain the load, and we can sustain the load even of the next stage of growth, right? That we anticipate.
Okay.
Inevitably, we would discover that one system or the other doesn't actually sustain. It was very rarely Venice, but sometimes it was. And then that's a bad place to be. When you're designated as the team which is the load test blocker, then all eyes are on you, and you really have to fix it quickly. So yeah, that's definitely something we exercised because having reliability mechanisms that you do not regularly test, it basically means you don't have reliability mechanisms, right? Because by the time you need them, they're not going to work anymore.
Okay, great. Thank you for sharing. So what I hear you saying is that, okay, there are a handful of components. First of all, it was the PubSub part, which was distributed, but actually all of the parts were distributed. And then the PubSub was used also as a replication mechanism, but also in order to, among nodes, but also in order to save the data. And then there were multiple other, I'll not just name them because I'll just probably miss some of them. in order to ensure that the data is properly kept and actually used, you had weekly tests or
load tests.
Yeah. Or using the Chaos Monkey pattern that was made well known by Netflix. Well, I think the technical term for this is called playing with fire. And I'm happy to hear that somebody's doing it to make sure that things are actually okay. Just to fully understand what will be, I don't know, let's say, probably it's not something that is used in practice, but let's say we have to place in Venice, or using this system, we have to put in place a new record. Based on our previous conversation, I know that usually it was the derived data. It wasn't data that was generated by a human, so they are mostly about machines. But if we just imagine that we would like to store something in, what would be the normal flow of writing and then reading it to just have a full picture of how the information is flowing from one side to another?
Yeah, good question. Venice is a little bit different than many other data systems in that regard. So that's a very good question to lean into. Venice, we can say, is a derived data system, which means the data it hosts has been machine generated, you could say, rather than user generated. That's not a hard rule. You could put user generated data in it if you wanted. It's just not as well suited for that. And Venice is not alone. There are many derived data systems, like, for example, Apache Pinot is another derived data system. The pattern that we see in general with derived data systems is that their write path, the way that you write into the system, is typically asynchronous. So that means the data gets loaded from a pub sub like Kafka, or maybe it gets loaded from a dump of files that were generated offline, like in some sort of job, like maybe a daily job or hourly job or weekly job. So it's either batch ingestion or stream ingestion. And sometimes it's both, right? So in Venice, we supported all permutations of these various derived data ingestion modes. So you could have your data come fully from a stream processor, for example, or you could have it come from a batch processor, or you could do both. You could have the data come once a day from a batch processor, but then in between the batch pushes, you would have a stream processor that's refreshing it as well. And then there's a bunch of different variants of that, right? Like you could say the stream processor refreshes just a subset of the columns of the table, and the rest of the columns are batch only, stuff like that. Venice would orchestrate all of these data ingestion scenarios out of the box. The key thing to remember is that because the data comes in asynchronously, it comes in through a pub sub, it can support very high ingestion throughput. But in exchange, again, we talk about trade-offs. This is what data systems are all about. The trade-off in this case is that because you're writing asynchronously to the system, you lose strong consistency, right? Or the technical term would be linearizability, right? So that means another way that we say it sometimes is read your own writes. So you do a write operation to the system. You can get an acknowledgement that the write is durable, right? You have attained durability, but the durability is only the durability provided by the write ahead log, which is Kafka. At that point, the data is not yet indexed into the system. It's not yet readable. So that's the design decision we made there. And like I said, Venice is not unique. Like other systems work similarly, like Apache Pinot is pretty similar to that also. So it's not fully unique, but it's still a little bit uncommon, right? Like, because in a traditional database, like let's say like Postgres, you also have a write ahead log, but the write ahead log is embedded inside of the Postgres process. And then the acknowledgement that you get when you do a write request, let's say you do an insert or an update, the acknowledgement you get is after the data was persisted to the write ahead log for durability, but also after Postgres updated all of its in-memory indices, right? So when you write to Postgres, you do get read your own write guarantees. You do get linearizability because Postgres has been designed to cater to primary data use cases. And in primary data, typically you do want to have that type of consistency guarantee, right? So that's the nuance between derived data and primary data, I would say.
Okay.
Or one of the nuances, at least.
The thing that is spinning in my head is a theorem that almost never I understood it. So I usually have like 5 to 10 minutes when I understand it, and then I forget about it. And that's the CAP theorem. And that's probably
Right.
the first 3 letters that are very important in distributed systems. So the main reason for that is that you have to choose 2 of the 3 letters usually when designing a distributed system. And
Yeah.
what would be the permutations of this? How would they look from your point of view when dealing with data? Because data is sensible and it has gravity. And when you're talking about global scale, you spoke about having multiple data centers. So how do you make sure that a long time ago, 2 to 3 years ago, I was just very surprised by the way how the data was replicated. In case of Amazon, I had an order in one browser. I can see the order on my phone. I couldn't see it. And then in a different browser, I got a big, it depends on that. So, and that's the example that I usually have with CAP theorem. How did you look at that when looking at it practically? Because you cannot play with those things like that.
Right. So the CAP theorem basically says there are 3 properties we care for: consistency, which in what we were discussing earlier in that context means read your own writes, or linearizability, right? That's what consistency means in the CAP theorem. Availability, and the P stands for partition tolerance. But there's a catch. In the CAP theorem, it says pick 2 out of 3, but one of the 2 you pick must be partition tolerance. So then the only real choices you have are CP or AP, right? Consistent and partition tolerant, or available and partition tolerant. That's what the theorem says. Now, in practice, the partition tolerance here means a network partition. So that means you are cut off from the database, or maybe the distributed database itself has some of its replicas cut off from the others, or some kind of scenario like that where some machine is unable to contact another machine, basically, right? That's what partition tolerance means, is how do you deal with that? This comes up during failure scenarios, right? Which means if you do not have a network partition, also called a net split, if you do not have a net split, then you could have a system that offers both the A and the P, right? It could be available, the A and the C. It could be available and consistent while there are no failures, right? Then when the failure occurs, you have to sacrifice one or the other. In terms of Venice, and I would say probably derived data systems in general, there is maybe a different way to think about it, which is, well, those systems are certainly highly available, right? So they are AP in that sense, but because the design choices that we explored earlier have made it so that our write path is asynchronous, and we've sacrificed strong consistency and linearizability from the get-go, right? We've already sacrificed this like at the drawing board level. It's not a matter of suffering a network partition that makes us lose consistency. It's almost as if we were continuously network partitioned in a sense, right? It's not like quite the same, but it's almost like that in the sense that it's almost as if the network route through which your packets must be transmitted for all of your write requests, that path always has a high latency, right? And so in a sense, it's as if from the point of view of a traditional database, it's as if that functionality is continuously degraded. So you never have consistency. The C in the cat theorem is lost like continuously. Interestingly, at least it's interesting to me, I don't know about others, but interestingly, this does not only apply to derived data systems. It can also apply to primary data systems that are multi-region and architected in a way to be multi-leader, right? And I think that's probably what you've experienced with the Amazon shopping cart example that you gave. It could be that your laptop is connected to one data center, let's say US East 1 or whatever, and then your phone, for some reason, is going to another data center, like maybe it's connecting to Europe. And like for some reason, you're going across the Atlantic with your laptop and you're connecting locally with your phone, right, to a closer data center, let's say, assuming you're in Europe, right? And so there is also replication going in both directions between these data centers, but it's asynchronous. So it could be that you add something to your shopping cart over here and it's not yet replicated over there, right? And so for those scenarios where you have a multi-leader replicated system, you also are, in a sense, in a situation where you have continuous high write latency between the regions. So that can be an interesting kind of design trade-off. Obviously, you get great reliability characteristics from being present in multiple regions. That improves your availability profile. But it does mean you're sacrificing consistency and not just during outages. You're sacrificing it continuously.
Yeah. So we have to choose our poison wisely and see exactly what's actually the important part. Okay. Thank you. Thank you for the explanation. So given that we are looking at most half an hour conversation, half of this conversation, I understood the cap theorem, as I told you that my span of remembering the cap theorem explanation is like at most a quarter of an hour. So thank you for that, Felix. It's makes me feel
You'll
better.
remember it for another 5 minutes after we're done.
Yeah. Yeah, thank you. The last question for me is one thing that I failed to ask you last time is you spoke about the two choices of having the two different engines that you and your team had implemented. And I know during the hackathon, I think you chose to give it a try, and rather than using RocksDB, try to use DuckDB. Now, if you look at them, they are a bit different. The first one is a key value pair, and the other one is an SQL engine to just oversimplify things. Given that you're talking about mostly machine-generated data, and you're talking about huge quantities, as you mentioned, batch processing and even stream, why would you need SQL?
Yeah, it's a good question. So you're right that this was integrated in a hackathon project. So in a sense, it was a way to test if our abstractions were flexible enough and so on, kind of a theoretical experiment in a sense. In terms of, and it did work, like we were able to get the Venice data into DuckDB instances that we could then query with arbitrary SQL. In terms of real world scenarios, I don't think we've used it in any real production use case yet. It is available there in open source if people want to try it out, the Venice DuckDB integration. But DuckDB is an incredibly flexible system, right? It's a very impressive project. Every time I've worked with it, I really enjoyed it. It has a bunch of different extensions. So you can do many, many things with it, including You can even do some vector type work like search and stuff like that. And these are things that could be interesting from the Venice point of view. Like Venice already has a little bit of built-in vector math kind of computation so that we can make those workloads more efficient. But it's a little bit basic, right? Like we developed this before the big wave of like vector databases that have exploded on the scene in the past 5 years. We had vector math running in the Venice servers since maybe 2019, I want to say. I think that's right. So a little bit before the rest of the industry kind of got on that bandwagon, but we also did not really update it much since then. So it's a little bit earlier, but a little bit more primitive in terms of scope of capabilities. By bringing in DuckDB, now we have like all of these extensions that we could kind of pull into the mix for free, so to speak. Nothing's ever free. Like there's always a trade-off, but for free between quotes, right? So that's one motivation. Another motivation we had was just like data exploration and debugging and stuff like that. Like sometimes you want to understand like what is the shape of your data? Like what is the cardinality of values in a given column? Regularly, we had some internal users that were asking us like, hey, look, my Venice data is populated by these stream processors. I should know what's in there, but now I have a doubt. Like maybe it's not quite what I expected that's going in there. And then they would ask us to like turn on the ETL so that the data gets loaded out of Venice and into the grid. And then they would use like offline tools like Spark or whatever to query that. So all of that workflow worked, but it was a little tedious, like high inertia. And this is one more option, right? Where you could, if the data set is small enough, or if you could get the answer you need out of just one partition of your data set, let's say, you could load that into DuckDB and then run queries like very fast and then get the answers you need about like, let's say what's the max value in that column or like those kinds of aggregation queries that DuckDB does very fast. So these were kind of the initial use cases we were thinking of. But like I said, DuckDB is so flexible that there's probably a lot more that I'm not even thinking of. But we'll see.
Yeah, pretty much it meets the reasoning in my head. That was more like some kind of analytics and some kind of just taking probes of data. So, okay, thank you for sharing, and thank you for taking the time to have yet another conversation, Felix.
Yeah, my pleasure, Olimpiu. It's always fun chatting with you.
Thanks for listening to this episode of the GOTO podcast. Head over to gotopia.tech to discover lots more content from the brightest minds in software development.